Dear all, I am Dr. B. Malati, Associate Professor, ECE Department, SR University, Warangal. Today I am going to present a lecture on EMG signal measurement and analysis. It is going to be simulated with the Python code and it is done in the Google Colab platform. So now let me explain the code. So already I have pasted the code and got the output. So line by line explanation I am going to give now. So the title is EMG signal measurement and analysis. First one, import numpy as NP. So numpy is the Python library used for numerical computations, and import matplotlib.pyplot as PLT. Matplotlib is a library used for plotting graphs. From scipy.signal import butter filterfield welch. So scipy is a scientific computing library. Signal is a module inside scipy used for signal processing. We are using the functions butter, filterfield and welch graph. Welch periodogram will be used in the case of EMG signal analysis. And then simulation parameters. Fs is equal to 1000. That is sampling frequency in hertz, 1000. Duration is equal to 5. That is 5-second duration. T equal to np dot range open bracket 0 comma duration comma 1 by fs. Here we are assigning the time in seconds. That is time vector we are defining. So it is starting from 0 and then it is duration. How many duration? Normally 5 seconds. So 0 comma 5 you can write. So it can be variable. That is why duration and duration equal to 5 seconds. So 0 up to 5. So this 5 second will be divided into so many parts. So how many parts means based on the 1000 of sampling frequency. So 5 by 1000. So 5 by 5 by 1000. So here it is equal to 0.001. So here 1 by fs in the range of 1 by fs. This 5 second will be divided. So 1 by 1000 is equal to 0.001. So how you will opt for the components from 0 to 5? 0, 0.001, 0.002, up to 4.999 and then entered with the 5. So it increases in steps of 0.001 second. That is 1 millisecond duration up to 5 seconds. And then simulated EMG signal. So EMG is the random high frequency activity. So the frequency varies from 20 to 250 Hz. So EMG is the random frequency. So it varies from 20 to 450 Hz. And then NP dot random dot seed 0. This line sets the random seed for numpy, and it ensures the random numbers generated are the same every time you run the code. And normally the random numbers change each run, but in Python it makes the output reproducible. So this is what the meaning for this function. and then EMG underscore raw. It is equal to NP dot random dot normal and open bracket 0, comma 1, comma LENT. This generates a random signal of mean equal to 0, standard deviation equal to 1 and number of sample equal to LENT. So LAN open bracket T, it is equal to Fs into duration. So Fs we know 1000, duration we know it is 5 seconds. So LAN open bracket T is equal to 5000. That is what the meaning. Then simulate muscle contraction burst. Burst equal to NP dot zeros LENT. So NP dot zeros, open bracket, close bracket. So in between function. So it creates an array filled with the zeros. So length equal to LAN open bracket T, that is same length as of the input signal. So whatever the time interval for the input signal, the same thing is maintained for the burst signal also. That is that random signal we are taking now for this signal also. And if Fs is equal to 1000, duration is equal to 5, LENT is equal to 5000, then burst is equal to 0, comma 0, comma 0 up to 0. That zeros occur 5000 time. That is what the burst signal. This creates a mask signal. There is no activity everywhere. So burst, next one, burst int 1 into Fs, int 3 into Fs is equal to 1. Now we modify part of the burst signal, part of the burst signal. Step by step, it is 1 into Fs. 1 into Fs is equal to 1 into 1000 equal to 1000. Then 3 into Fs. So 3 into 1000 equal to 3000. So this becomes burst starting from 1000 up to 3000, which is equal to 1. Now what is the meaning? From 1 second to 3 seconds. Change the values from 0 to 1. Now the burst looks like time. So 0 to 1 second 0. 1 to 3 second 1. 3 to 5 second 0. This creates a muscle activation window between 1 second and 3 second. Now EMG signal equal to EMG raw into burst. Since outside 1 to 3 second, burst is equal to 0, signal becomes 0. And in between 1 to 3 second, burst equal to 1, signal remains original noise. So, effectively, EMG activity only exists from 1 second to 3 second. Before and after, signal is 0. So 1 to 3 second is taken as a window. That is the windowing property. This simulates a muscle contraction burst. That is 0 to 1 second reset. 1 to 3 second muscle active. 3 to 5 second rest. So add motion artifact. Next one, low frequency noise. Motion noise is equal to 0.5 into NP sine 2 pi ft. F is equal to 5. So NP sine, what is the meaning? This generates a sine wave. A sine wave formula is A sine omega t, where omega equal to 2 pi ft. So 2 pi f is equal to 5 into t. This means frequency equal to 5. So the signal oscillates 5 cycles per second. If duration is equal to 5 seconds, total cycle is equal to 5 into 5, 25 cycles. Then 0.5 into this sets the amplitude 0.5. So the sine wave varies between plus 0.5 and minus 0.5. Final noisy EMG signal. EMG noisy, it is equal to EMG signal plus motion noise, and band pass filter 22 to 450 Hertz. Define band pass filter signal, low cut, high cut, FS, order equal to 4. This defines a band pass filter function. The parameters are signal, that is input signal EMG, then low cut, lower cutoff frequency, then high cut, upper cutoff frequency, then FS, sampling frequency, order equal to 4, that is fourth order filter default. A band pass filter keeps frequency between low cut and high cut and remove others. So below low cut, all components will be removed. Above high cut, all components will be removed. And then Nyquist is equal to 0.5 into Fs. So F1 Nyquist frequency is equal to Fs by 2, half of the sampling frequency. Here in this code we have adopted Fs is equal to 1000. So 1000 by 2 is equal to 500. Then low equal to low cut by Nyquist. So it is standardized as low cut divided by Fs by 2. In the same way, high is equal to. So it is also normalized high cutoff frequency, high cut divided by normalized Fs by 2. So the digital filters require cutoff frequencies between 0 and 1. If low cut equal to 20 Hz, if low cut equal to 20 Hz and high cut equal to 450 Hz, then Nyquist is equal to 500 Hz, then low cut equal to 20 by 500, it is equal to 0.04, and high cut equal to 450 by 500, it is equal to 0.9. Next one we have to generate filter functions B, A. So it is numerator of the filter coefficient, and then A is the denominator of the filter coefficient. It is equal to butter, open bracket, order. So it is 4, low, high, Butterworth filter type. It is equal to band pass filter, which is adopted in this code. This creates a Butterworth band pass filter. So this line, what is the meaning? This creates this line creates a Butterworth band pass filter of order 4. Low, high frequency band, that is pass band. So type of the Butterworth filter is band pass filter. B and A are filter coefficients, numerator and denominator. And return filter B, A, signal. So what about filter function? It applies filter forward and backward, to and fro. So two sides it will be applied, and it removes phase distortion. It It preserves waveform shape. This is a very important. This is very important for EMG. This filter function. Next one, EMG filtered is equal to bandpass filter, EMG noisy, 20, 450, FS. Now, what is the meaning for this code? It calls the bandpass filter function and stores the result in EMG filtered. It means EMG noisy gives input signal, that means EMG original raw EMG and noise, that is added with noise. 20 we know lower cutoff frequency. 450 also we know it is upper cutoff frequency. Fs sampling frequency, that is here 1000 Hz adapter. Then rectification. EMG rectified is equal to NP dot ABS open bracket EMG filtered. So NP dot, so NP we know numpy for Python. ABS means absolute value. It converts all negative values to positive. Positive values remains unchanged. And for this, a formula is given. That means determinant x, the value is x if x value is greater than or equal to 0, and the determinant x value is equal to minus x if x is less than 0, and raw mg is defined as 0.5. Then minus 0.8, then 0.3, minus 0.6. After rectification, the rectified EMG will become 0.5, 0.8, 0.3, 0.6. Now what I am telling, if minus are available, that is negative value is available, it will become positive after rectification. If we calculate average of raw EMG, then mean value is equal to 0 because positive and negatives cancel out. But after rectification, mean value is greater than 0. Now the signal reflects muscle activity level, signal energy. Next one, envelope detection. So that is low pass filter, open bracket, low pass filter, envelope detection. Low pass is a 10 hertz. Low pass is 10 hertz. Define low pass underscore filter signal, cutoff, fs, order equal to 4. Now, what is the meaning for this? This defines a low pass filter function. So here cutoff is equal to cutoff frequency. Signal is input signal, rectified signal. See, notice here we have to notice that it is not a raw EMG signal. After rectification, that particular EMG signal is applied with the low pass filter. So before that we have applied band pass filter. Now low pass filter is going to be applied. So cutoff is the cutoff frequency and sampling frequency is Fs, order of the filter is equal to 4. A low pass filter keeps low frequencies and removes high frequencies. So Nyquist is equal to half of the Fs. Now here it is a digitization. That is why we need to talk about the digital filter. Digital filters require normalized frequency 0 to 1. If cutoff equal to 10 Hz, Nyquist is equal to 500 Hz, then normal cutoff equal to 10 by 500. It is equal to 0.02. So normal cutoff equal to cutoff by Nyquist. So this formula I am applying, I am telling that it is 10 by 500. 500. So that value is 0.02. Next one, B, comma A, butter. So filter coefficients, numerator, denominator. Butterworth filter, type is low pass filter. Order, comma, normal cutoff. So order we know it is 4. Then return field A, comma, signal. And then EMG envelope equal to low pass filter, EMG rectified, comma, 10, comma, Fs. Now the meaning for this. Input is rectified EMG, I told you already, and it is applied with low pass filter of cutoff frequency 10 Hz. So here low pass cutoff frequency is 10 Hz, already mentioned. It keeps only very low frequencies. It removes fast oscillations because low. And then RMS calculation. So window size is equal to 10 int open bracket 0.1 into Fs. That means 100 ms 100 millisecond window, because it is 100,000 into zero point 0.1, so 100 millisecond window. So the meaning for this line is 0.1 second equal to 100 millisecond. Multiply by Fs, sampling frequency. Sampling frequency is equal to 1000. So it is 100 millisecond. So now window size is equal to 0.1 into 1000. It is 100 samples. 100 samples. Now, so this creates a 100 sample moving window. So within a window 100 sample, that is a 100 sample moving window, which equals 100 millisecond duration. So the window occupies 100 millisecond time interval. That is what the meaning. And then this window will be used for RMS calculation. Next one, RMS is equal to NP square root NP dot convolve EMG underscore filtered power 2. NP1 open bracket window underscore size divided by window size, comma, mode is equal to same. Now, what is the meaning? This computes the moving RMS, that means root mean square of the EMG signal. EMG filtered power 2. This makes all values positive. It represents signal power, that is multiplied by 2 of t. 2 of t. 2 of t. So NP dot ones. Window size divided by window size. Window size divided by window size. So how we will write 1 by 100, comma 1 by 100, comma 1 by 100. So up to last value is also 1 by 100. This is a moving average filter. So next one, NP dot convolve. MP dot convolve. MP dot convolve. Signal comma window comma mode equal to same. Mode equal to same. This slides the window across the signal. It computes average of the squared values. It produces a smooth power signal. Mode equal to same. It means output length is equal to same as the input. Previously in our course we have used LEN open bracket T close bracket. So instead of that, it is also possible to use mode equal to same. Both carry the same value, same meaning. So finally RMS value. What is RMS value? It is the formula only. It is equal to square root of 1 by n sigma I equal to 1 to n x square of I. The function is I. So it computes the root mean square over 100 millisecond window, and then frequency spectrum power spectral density. Frequency dot BSD, it is equal to Wells EMG underscore filtered comma fs comma n per sec is equal to 1024. Then what is the meaning for this? EMG filtered is equal to input signal. Fs is sampling frequency 1000 Hz. N per sec is equal to 1024. Segment length for analysis, it is equal to 1024. We have assumed 1000, it is standard value we have taken. And Welch method, it splits the signal into segments. Each segment length is 1024 samples. It computes a fast Fourier transform on each segment, then averages them. So next, larger n per seg, larger n per seg. Better frequency resolution, less smooth power spectrum density. Suppose n per sec is smaller, more averaging, smoother PSD, lower frequency resolution. Then plot results. PLT dot figure open bracket, figure size 15, 12. So the signal, the graph size is 15. That means width is 15, height is 12. Then subplot PLT dot subplot 5, 1, 1. 5 rows, 1 column. The first position. PLT dot plot time, EMG noisy. So horizontal axis timer, vertical axis EMG noisy. It is in magnitude only. So x limit is 0, 5. So starting from 0, ending with 5. So title of this total diagram is graph is raw noisy EMG signal, and then PLT dot subplot 5, 1, second position. What is the name given to that plot is filtered EMG signal 20 to 450 Hz, and a limit also 0 to 5 only. But how it is drawn, the time versus EMG filtered. Here in y-axis EMG noisy, here filtered signal we are taking. Then PLT dot subplot 5, 1, 3. Third position EMG rectified signal, time versus EMG rectified signal. So the title is rectified EMG signal. The same limit for x-axis 0 to 5. And then fourth position, it is taken time versus EMG envelope. So the title given to this EMG envelope muscle activation. X limit is applied to here also 0 to 5. And then subplot 5, 1, 5, fifth position, plot semi-loggy frequency, ATST. So this plot, the title is power spectral density of EMG, and X label is frequency, Y label is power by frequency, that is E square by F. And then tight layout. So equally spaced all diagrams, and then all plots are shown. It is visible, and then the output numerical answer should be displayed as print raised RMS value. Actually, the RMS value equation I told you, RMP dot mean RMS. So here, what is the value? It should be printed out after the calculation. It is raw noise EMG as we have plotted printed in the graph. Second one filtered EMG. Third one rectified. Fourth one EMG envelope muscle activation. Then PSD. So power spectral density of EMG. So finally RMS value is calculated as 0.35. So it is 0.35, otherwise 0.36. Thank you.